Section 3.4. Let us go back to our systems of differential equations. Homogeneous, linear with constant coefficients. Remember, we can rewrite this system in this form. X dot is equal to AX, where X is this and A is this. Now, Theorem 4, existence uniqueness theorem. Theorem 4 says that if we combine such a system with this initial condition, the resulting initial value problem has a unique solution. Theorem 5. Theorem 5 is very short. It consists of only one sentence, but this sentence is so telling. The dimension of the space V of all solutions of this system is n. Here is what this means. Remember, what is the dimension? The dimension is the smallest number of linearly independent vectors that span the whole vector space. In our case, this means the following. Any solution of this system can be written as a linear combination of n linearly independent particular solutions. Moreover, if instead of n linearly independent particular solutions, we consider n minus 1 particular solutions, now not any solution of this equation can be written as their linear combination, because n is the smallest number of linearly independent vectors which span the whole vector space. For example, take a look at this system. X dot is equal to AX. We solved the system and we came up with the following result, this. So we have two particular solutions. Any solution can be written as their linear combination. What is left is the following. You can say, wait a second. Since over here we have functions, how to prove rigorously that these two matrix columns are linearly independent? Note that in the previous section over here, we discussed a linear independence of matrix columns that have real numbers as entries. But what if instead of real numbers we have functions? For example, take a look at this. Particular solution number 1, particular solution number 2. Components are functions. How to determine whether or not these matrix columns are independent? Note that if we apply this approach, our system will be pretty heavy. Instead of numbers in front of all these C's, we'll get functions. It's really hard to deal with such a system. Theorem 6 helps us to determine whether or not our particular solutions are independent. Theorem 6 says the following. If we have k particular solutions of our system, these k particular solutions are linearly independent if and only if these matrix columns are linearly independent. T0 is a number. Which number? Any number, convenient for us. For example, take a look at this. Here's particular solution number 1, particular solution number 2. Replace t by any convenient number. For example, by 0. If we replace t by 0 here, 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 and here, this becomes this. and then this matrix column becomes this matrix column. Note that these two matrix columns are linearly independent because they are not constant multiples of each other. Here's why. If, for example, this is a constant multiple of this, then 1 is equal to lambda times 1. Therefore, lambda is equal to 1. But if lambda is equal to 1, this times lambda is negative 1/2, which gives us a contradiction. It should be negative 3/2. In the same fashion, we show that this is not a constant multiple of this. So these two matrix columns are linearly independent. Therefore, these two matrix columns are linearly independent by Theorem 6. Important remark. Theorem 6 can be used for testing independence only. We cannot use it to test dependence. One can say, why is that? This is if and only if statement. However, note that Theorem 6 consists of 3 sentences, not just one sentence. Therefore, in order to use it as the dependence test, we have to negate the whole thing, including sentence number 2. And now, if we negate sentence number 2, it becomes if for all t's these are dependent, then these matrix columns are dependent. But since we have to prove that these columns are dependent for all t's, it is not enough to plug in a finite number of values for t. Take a look at this example. Note that if we replace x by 0, the resulting matrix columns are dependent. We show it in the appendix. However, as I said, it does not necessarily mean that the original matrix columns are also dependent. By the way, this problem was given in fall 2019 and the average was pretty low because, again, students plugged in 0. They concluded that the resulting columns are dependent and therefore they said the original matrix columns are dependent. However, in the remark, we say the theorem cannot be used for testing dependence. It is easy to show that even if we plug in pi, or pi over 2, or pi over 4, the resulting matrix columns will be dependent. We show it in the appendix. However, if we replace x by 1, the resulting matrix columns are independent. Therefore, these matrix columns are independent by Theorem 6. Now you can say, then how do we prove dependence? Take a look at this example. Here we show that these 3 matrix columns are dependent. Here is why. Note that sine square plus cosine square is 1. X square plus 2x plus 1 is x plus 1 square. E2x plus E2 negative x is obviously this. Conclusion, x3 is equal to x1 plus x2. Vectors are dependent. Now, on a test, if I give you several matrix columns, first look at identities. If you recognize identities everywhere, then matrix columns are dependent. It's exactly what we have here. However, looking at the previous example, We don't know how to combine these two functions in order to obtain one. We don't know how to combine these two functions in order to obtain sine square. This is an indication that vectors are independent. Then start plugging in numbers. Plug in numbers until you get matrix columns with real components with numbers everywhere, such that these matrix columns are independent. Folks, questions?
You said that if we ever like see identities in every vector, then or in like our vectors, it's always going to be dependent, right?
Yes, absolutely.
Okay. Thank you.
So if you recognize an identity in each row, then it is impossible to find X such that the resulting matrix columns are independent.
Thank you.
Other questions?
So, Professor, in this case, since x3, the vector x3 is a combination of vector x1 and x2, right? Would
Yes.
you say that all three of them are linearly dependent, or just x3 is linearly dependent?
When we say dependent or independent, we are talking about the whole set.
Okay, thank you.
Other questions?
So is that the only way to prove that they are dependent?
I would say yes. You have to look at identities because plugging in numbers fundamentally does not work. If you negate, as I said, this, instead of select a convenient, you'll have to check dependence for all values of t, which is impossible.
What do you mean by identities?
Well, there are identities in trigonometry and in college algebra. For example, sine square plus cosine square is 1. This is an identity. An identity means no matter what is x, the left-hand side is equal to the right-hand side. Was that your question?
Yes, thank you.
Other questions?
And you said for the previous problem, since there isn't an identity, we just try plugging in values?
Yes, absolutely. So we just don't know how to combine each x and each negative x in order to get 1. We've never seen such an identity. C1 each x plus C2 each negative x is equal to 1. So if I give you a problem that involves identities, these identities will be more or less straightforward. Everybody knows sine square plus cosine square. Everybody knows x squared plus 2x plus 1. If you do not see something obvious, plug in numbers until you get linearly independent columns.
Thank you.
Other questions?
So for the last example, if x3 had one value that wasn't equal to like a combination of x1 and x2, could we then say that this was independent?
Yes, independent, absolutely. For example, if instead of this you put, say, 2 e2x plus e2 negative x, the resulting matrix columns will be independent. Plug in a number and you will see it. All right. Now, let us go back to 2x2 systems of differential equations. We discussed these systems in section 3.1. Over here, if you look at the remark, this remark tells us how to solve any such a system. Either we solve equation number 1 for x2 and plug in into the second equation, or solve equation number 2 for x1 and plug in into the first equation. This is exactly what we do here. Equation number 1 is already solved for x2. So we just replace x2 here and here by x1 prime. It's exactly what happened here. Then move the right-hand side to the left, done. And then we know how to solve this equation. These are two particular solutions. Here is the general solution. Now, this is x1. In order to find x2, we use first equation of our system. x2 is x1 prime. We find the derivative of x1, done. And then the general solution of our system is the following matrix column, x1, x2. Over here, finally, we split it into two pieces and factor out C1 and C2. This is method 1. However, it turns out that the combination of theorems 5 and 6, these two theorems, allows us to solve this system in a little bit different way. Take a look. These computations are not as heavy as these computations. Here's what we do in method 2. We find two particular solutions of our system. Note that this is boldface X, this is boldface X. These are particular solutions of our system separately. So boldface x1 is x1, 1, x2, 1. This is a particular solution of our equation number 1. We replace this by e2 negative t. We replace x2 by x1 prime, thanks to equation number 1 of our system, and then find the derivative of this, done. We do same thing over here, but now x1, 2 is the second particular solution of our equation. We find the derivative, done. This is particular solution number 1 of our system. This is particular solution number 2 of our system. The general solution is C1 times this plus C2 times this. Note that our computations here and here are a little bit easier than over here because of two reasons. Well, reason number 1, we don't really show how we jump from here to here. Over here we show all steps, chain rule, product rule. Here, since everything is done in method number 1, we don't do it here and don't do it here. However, there is another reason why these computations look lighter. There is no C1, there is no C2. We don't take the derivative of the whole thing at once, including C1, C2. Here, we take the derivative of portion number 1 separately and portion number 2 separately. Then we multiply this by C1 and this by C2. However, this is not the end of the story in method number 2. In method number 2, before we multiply this by C1 and this by C2, in order to create the general solution, we have to prove that these two matrix columns are linearly independent. It's exactly what we show here. We use Theorem 6. We plug in a convenient number instead of t here, here, everywhere. We get this and this, t is 0. Then, since these two matrix columns are not constant multiples of each other, these two matrix columns are linearly independent, and therefore these two matrix columns are linearly independent. Therefore, this is the general solution. By the way, over here we show that these two matrix columns are linearly independent in two different ways. The easiest way is to note that these two matrix columns are not constant multiples of each other. Here's why. Note that this is not a constant multiple of this because 1 is not equal to 0 times lambda. Similarly, this is not a constant multiple of this because if 0 is a constant multiple of 1, then lambda is equal to 0. But if lambda is equal to 0, negative 1 times this lambda is 0. But we need 1. So contradiction. This is the easiest way to show that these two matrix columns are linearly independent. We can also use definition of independence. Multiply this by C1, multiply this by C2, add up, move C1 inside, done, move C2 inside, done, add these two columns, done. Note that this is equal to 0 if and only if both C1 and C2 are equal to 0, which means these two columns are independent. Folks, any questions here?
Yes. So if you do method 2, and let's say you get it's linearly dependent, what would you do?
Well, great question. In short, if you apply this theorem, you will always get linearly independent solutions. We do all these computations in this section just to remind you that independence has to be proven. We're trying to solve this problem in the rigorous possible way. But once again, on a test, if you prefer method number 2, just apply this. One can show that if you choose as particular solutions of our homogeneous equation, either these functions, or these functions, or these functions, and then apply this approach, the resulting matrix columns will necessarily be independent.
Okay.
Did I answer the question?
Yes, thank you.
Other questions?
So what role does theorem 5 play in method 2?
Theorem 5 tells us that since our system is a 2 by 2 system, in order to create its general solution, we need only 2 particular linearly independent solutions. It's exactly what we do here. Over here, thanks to this part, this is a particular solution and this is a particular solution. Thanks to this part, these two solutions are linearly independent. Therefore, C1 x1 plus C2 x2 is the general solution. Does this make sense?
Yes.
Other questions?
Professor, why are we why are we finding the derivative of the second row?
Great question. We find the derivative of x1 because equation number 1 of our system is x2 is equal to x1 prime. For example, if instead of this we have, say, x1 prime is equal to 5x2, then x2 is 1 over 5 x1 prime, and here we'll put 1 over 5 x1 prime, 1 over 5 x1 prime. Was that your question?
Yeah, thank you.
Very last thing. Over here, we consider the following initial value problem. Same system, and then initial condition. This initial condition allows us to find particular values of C1 and C2. Here's how we do it. Thanks to this, x of 0 is equal to this. Now, going back to formula 6, if in formula 6 we replace t everywhere by 0, this becomes C1 and this becomes C2 minus C1. So C1 is equal to 1. If we replace C1 by 1 and move it to the left, C2 is 1 plus 1, which is 2. And now I'll replace over here C1 by 1, C2 by 2, we get this. Folks, we are done with this section. Any questions?
Can you go over that last example one more time? I think I even just missed like the first. So you're saying that this is for the problem before, so you plugged in 0?
Yes. So this is same as this, written in matrix form. It is same system. But now, in addition to the system, we have initial value. So the whole thing is so-called initial value problem. System and initial condition. We will use this initial condition to determine values of C1 and C2 such that this satisfies not only this system, but also the initial condition.
But we already had the equations from the example before that.
So this is the general solution of the system alone without this condition. But now, in order to find C1 and C2, we use this condition. We find C1 and C2, this satisfies not only this, but also this.
Okay, I got it. Thank you.
Sure. Other questions?
Professor, where are you getting the second matrix from, the C1 and the C2 minus C1?
How do we get this?
Yeah.
So we replace T everywhere here by 0. Note that C2 times 0 is 0. This term disappears. And lastly, e to 0 power is 1. Also disappears. What is left is C2 minus C1. It's exactly what is written here. Was that your question?
Yeah.
Other questions?
Why does our solution for method 2 not have any constants with it?
Well, it does have constants. Note that this is not the end of the story. This is particular solution number 1 of our system. This is particular solution number 2 of our system. Then we show that these two particular solutions are independent, and then the final answer is at the end. Here is C1, here is C2.
Thank you.